The cold morning air of Seattle bit through the wool flight jackets of 11 men climbing aboard a gleaming aluminum prototype, serial number 41-0003, the second XB-29 Superfortress ever built. The date was February 18th, 1943. At the controls sat Edmund Turney Allen, better known as Eddie Allen, the most experienced four-engine test pilot in the world. A rare breed, he was both an engineer and a pilot, a man who understood the machines he flew at a molecular level. His co-pilot, Robert Dansfield, ran through the pre-flight checklist as the four massive Wright R-3350 engines coughed, sputtered, and then roared to life, each one generating over 2,000 horsepower, shaking the airframe with a violence that seemed barely controlled. Allen had already cheated death in this same aircraft. Just weeks earlier, an engine fire had nearly consumed the prototype in midair, flames licking at the wing structure, while smoke filled the cockpit. He had landed downwind, against every instinct and procedure, because there was no time to go around. The Army Air Forces had awarded him a rare civilian air medal for saving the aircraft instead of ordering his crew to bail out. But Eddie Allen knew something that the generals in Washington and the executives at Boeing were reluctant to admit publicly. This engine, this magnificent, terrifying Wright R-3350 Duplex Cyclone, was killing pilots faster than the Japanese ever would. At 12:09 Pacific wartime, the XB-29 lifted off from Boeing Field, the landing gear retracting into the polished aluminum belly as Allen climbed into the gray Seattle sky. Within minutes, the first engine fire erupted. The carbon dioxide extinguisher system triggered automatically, snuffing out the flames. A routine occurrence, Allen noted grimly. He had aborted flights for engine fires before. He banked the bomber back toward the field, setting up a long, curving approach. But this time, fate had written a different ending. Another fire ignited, this one fed not by engine failure, but by a design flaw no one had anticipated. Fuel had siphoned through faulty filler caps atop the wing, pooling invisibly in the wing structure. A length of instrument tubing, hot from contact with an exhaust manifold, created a slow-burning fuse that finally reached the pooled fuel. The left wing erupted. A large section of the leading edge blew away, scattering aluminum across Seattle's industrial district. Fire spread through the wing with terrifying speed. 3 crew members jumped, but they were too low. Their parachutes never had time to open. At 12:26, the XB-29 crashed into the Fry meat packing plant south of downtown Seattle and exploded. Nearly 5,000 gallons of aviation fuel created a fireball visible for miles. Eddie Allen, 10 of his crew, 20 factory workers inside the building, and a firefighter who responded to the blaze, all perished. Boeing's only other B-29 qualified pilot, who had flown as Allen's co-pilot on previous flights, saw enough. He quit the program. The crash sent shockwaves through the American military-industrial complex. This was not just a test aircraft. This was the future of strategic air power, the weapon that Army Air Forces General Henry Harley Arnold, known universally as Hap Arnold, had staked his entire reputation on. The B-29 program represented the most expensive military project of the entire war, eventually costing $3 billion, equivalent to $52 billion in today's currency. To put that in perspective, the Manhattan Project, which developed the atomic bombs that would eventually be dropped from B-29s, cost $1.9 billion. The bomber program exceeded the cost of building nuclear weapons by over $1 billion. And now, that investment was literally going up in flames. If you find this story of engineering struggle and wartime desperation compelling, please take a moment to subscribe to this channel and hit that notification bell. There is much more history to uncover together. The Wright R-3350 Duplex Cyclone was supposed to be the engine that would carry America to victory in the Pacific. On paper, it was a masterpiece of engineering ambition, 18 cylinders arranged in 2 rows, displacing nearly 3,350 cubic inches, the largest production aircraft engine in the world. Early models promised 2,200 horsepower at a time when half that output was considered impressive for contemporary engines like the Rolls-Royce Merlin. The R-3350 offered something else that strategic planners craved: exceptional fuel efficiency. For a bomber designed to fly thousands of miles to attack the Japanese home islands and return, fuel consumption was not just a specification, it was a strategic necessity. The Wright R-3350 first ran in May of 1937, developed from the successful lineage of Wright Cyclone engines that had powered everything from Lindbergh's Spirit of St. Louis to the B-29 Flying Fortress. But while its predecessors had been refined over years of peacetime development, the R-3350 would be forced into combat readiness in a fraction of that time. The engine would fly into war with problems that should have been identified and solved years earlier. This rush would cost hundreds of American lives. Understanding why the R-3350 became such a deadly engine requires understanding the corporate culture that produced it. Curtiss-Wright, the company that manufactured the engine, was the product of a 1929 merger between two aviation pioneers, the Curtiss Aeroplane Company and the Wright Aeronautical Corporation. By the late 1930s, the combined company had become one of the largest aircraft engine manufacturers in the world. But size bred complacency. The company's management structure was hierarchical to the point of paralysis. Everything important had to be cleared through Curtiss-Wright headquarters in the skyscrapers of Rockefeller Plaza in New York City. Division managers had no autonomy. Initiative was discouraged. Talented engineers and executives avoided the company because of its reputation for bureaucratic stagnation. The man who designed the R-3350's basic architecture was an immigrant German engineer named Rudolf Daub. Daub had grown up in the classic German apprenticeship system, where aspiring machinists learned their craft by carving camshafts from solid steel billets, using nothing but hand files. He brought that precision and craftsmanship to Wright Aeronautical, designing the successful R-2600 14-cylinder radial engine that would power aircraft like the B-25 Mitchell and the TBM Avenger torpedo bomber. The R-3350 was supposed to be his next masterpiece, an R-2600 on steroids, with 9 cylinders per row instead of 7. But corporate politics intervened. Daub was transferred to a different project, the ill-fated 42-cylinder Tornado engine, and the engineers who took over the R-3350 removed many of his original design features. Years later, when mechanics and engineers struggled to fix the R-3350's problems, they would go back to Daub's original drawings. In every case, restoring his features solved the problem. The fundamental issue with the R-3350 was heat. More specifically, the inability to dissipate it. An aircraft engine generating 2,200 horsepower produces an enormous amount of thermal energy. In a water-cooled engine like the Rolls-Royce Merlin, that heat is carried away by circulating coolant to radiators, where it can be dissipated into the airstream. But the R-3350 was air-cooled, relying on airflow through carefully designed baffles to carry heat away from the cylinder heads. The problem was that in a twin-row radial, the rear row of cylinders sits directly behind the front row. By the time cooling air reached those rear cylinders, it had already been heated by passing over the front row. The temperature differential between the coolest and hottest cylinders could exceed 150 degrees Fahrenheit. Cylinders 3, 5, 7, and 9 in the back row were particularly affected, running so hot that their exhaust valves would fail. The consequences of exhaust valve failure were catastrophic. When a valve unseated, it disrupted the careful choreography of combustion. Unburned fuel and superheated gases could escape in unpredictable directions. But the real killer was what happened next. The R-3350's crankcase was made of magnesium alloy, chosen because magnesium is light and incredibly strong. But magnesium has another property that made it the worst possible material for an engine prone to overheating. It is highly flammable. Once ignited, magnesium burns with a core temperature approaching 5,600 degrees Fahrenheit. That is hot enough to melt through steel. The fires burned so intensely that the onboard carbon dioxide extinguishers were worse than useless. Magnesium actually strips oxygen from carbon dioxide, feeding the flames instead of smothering them. The fire would burn straight through the main wing spar in seconds, causing catastrophic wing failure. There was no surviving that kind of structural collapse. The statistics tell a grim story. Of 414 B-29s lost during the bombing campaign against Japan, 147 were lost to enemy action, flak and Japanese fighters. 267, nearly twice as many, were lost to engine fires, mechanical failures, takeoff crashes, and other operational causes. For every B-29 shot down by the enemy, almost 2 were destroyed by their own engines. The grim joke among B-29 crews was that Curtiss Wright was killing more Americans than the Japanese. Except it was not a joke. The problems with the R-3350 went beyond just cooling. The engine's reduction gear system, which slowed down the propeller to efficient speeds, was prone to catastrophic failure. The reduction gears in early R-3350s would strip and disintegrate after just a few dozen hours of operation. Nobody at Wright Aeronautical seemed interested in analyzing why. Band-aid fix after Band-aid fix was applied, none addressing the root cause. Finally, someone actually measured the tolerances in a production gear set and discovered the embarrassing truth. An automated gang drill press at the New Jersey factory that simultaneously bored the holes for a dozen planetary gear carrier shafts was badly out of alignment. The holes were being drilled in slightly wrong positions, creating stresses that would eventually destroy the gears. A team of experienced machinists was put to work drilling the holes by hand around the clock. The reduction gear problem largely went away. The fuel distribution system was equally problematic. The R-3350 used a downdraft carburetor with a poorly designed elbow entrance to the supercharger. This created uneven fuel-air mixtures across the 18 cylinders. Some cylinders ran lean, others rich. Lean mixtures caused backfires that could ignite fuel pooled in the induction system, setting the magnesium supercharger case ablaze. Rich mixtures fouled spark plugs and reduced power. The only solution was direct fuel injection, spraying fuel directly into each cylinder rather than relying on a carburetor to mix fuel and air for all cylinders at once. But implementing direct fuel injection across thousands of engines in the field was a massive engineering and logistics challenge. The workforce that built these engines was itself a problem. Wright Aeronautical had established its new R-3350 factory in New Jersey near New York City rather than in a location like Kansas, where there was a pool of experienced aviation craftspeople. The company paid low wages, starting workers at the equivalent of $9.40 per hour in modern money, and had to compete with New York shipyards for labor. The result was high turnover, chronic absenteeism, and low morale. In the words of one historian, Wright used the dregs of the workforce to manufacture the most complex piece of mass-produced machinery built at that time. The best R-3350 factory was not even operated by Wright. It was a massive plant in Chicago, built by Chrysler and run by its Dodge division. Dodge-built engines became the gold standard among B-29 crews, though even they were far from reliable. In the summer of 1943, Congress had finally had enough. General Arnold was ordered to convene a high-level committee to investigate Curtiss Wright's failures. The board included future Supreme Court Justice William Brennan, future New York City Mayor William O'Dwyer, and aircraft manufacturing pioneer James McDonnell. They found appalling managerial incompetence and a shockingly casual approach to what should have been the most critical engine program of the war. But the investigation, while damning, produced no immediate solutions. The war was not going to wait for corporate restructuring. By early 1944, General Arnold was growing desperate. He had promised that B-29s would begin bombing Japan as part of Operation Matterhorn, initially flying from bases in India and China. He needed at least 175 combat-ready Superfortresses. When he visited the Boeing factory in Wichita, Kansas, he walked down the assembly line and selected the 175th fuselage to bear his name, demanding it be delivered before March 1st. But when Arnold returned to Kansas on March 9th, he found no B-29s ready for combat, not one. Some aircraft had been sitting on the ramp for 2 months, waiting for parts that never arrived. Arnold was livid. What followed became known as the Battle of Kansas, an emergency mobilization of technical resources that represented one of the most remarkable industrial feats of the war. General Bennett Myers was given full authority to act in Arnold's name, with unlimited power to commandeer resources. Specialist ground crews and technicians were called in from all over the country. 600 workers were pulled directly from the Wichita assembly lines. Subcontractors were told to stop all work on non-B-29 components until their commitments were fulfilled. The modifications required were staggering. Every engine had to be pulled and rebuilt. The cowl flaps that controlled airflow had to be completely redesigned. Propeller governors needed adjustment. The fuel system required replumbing. The electrical system, with its 586,000 individual connections, had to be checked and resoldered. Steel reinforcement plates were added to strengthen internal structures. Entire rudders were replaced. Thousands of detailed changes had to be incorporated into aircraft that had already rolled off the assembly line. And all of this work had to be done outdoors, on the wind-swept Kansas prairie, during one of the bitterest winters on record. Mechanics worked through blizzards, their hands cracking from the cold, racing against a deadline that the Japanese knew nothing about. The Battle of Kansas succeeded, barely. B-29s began arriving in India in April of 1944, and the first combat mission flew on June 5th. But the engine problems had not been solved. They had merely been deferred. The tropical conditions of the Pacific Theater would prove even more brutal on the R-3350 than the test flights over Kansas and Washington. This is a good moment to remind you that if you are enjoying this deep dive into one of aviation's greatest engineering challenges, please like this video and consider subscribing. Your support makes this kind of detailed historical content possible. The B-29s deployed to the Pacific faced conditions that seemed designed to torture their engines. The coral runways of Pacific Island bases were constantly dusty, and that dust was sucked into engine intakes, abrading cylinder walls and contaminating lubricating oil. Temperatures on the ground routinely exceeded 100 degrees Fahrenheit before the morning missions even launched. The engines were already running hot before the aircraft even left the ground. Takeoffs were made at maximum gross weights, with fuel loads calculated to the gallon and bomb loads pushed to the limit, leaving no margin for error. The climb to bombing altitude was agonizing. B-29s were designed to fly at altitudes above enemy defenses, over 30,000 feet. But reaching those altitudes with a full bomb load meant long, slow climbs at high power settings with pilots and flight engineers watching the cylinder head temperature gauges like hawks watching prey. If temperatures exceeded 500 degrees Fahrenheit, valve failure became likely. The standard procedure was a delicate dance of adjusting cowl flaps, throttle settings, and mixture controls, trying to extract maximum climb rate without cooking the engines. Open the cowl flaps too much, and the drag would slow the climb. Close them too much, and the temperatures would spike. It was said that flying a B-29 formation was impossible. The aircraft flew in loose streams instead, each crew fighting their own private battle with their engines. 2 crew positions on the B-29 existed for a purpose found on no other bomber. The waist gunners, positioned in clear plastic blisters on each side of the aircraft, had remotely controlled 50 caliber turrets that they aimed through sophisticated analog computer gun sights. But their primary duty was not shooting at enemy fighters. Their primary duty was watching the engines and reporting fires and oil leaks. No other bomber in the war, American, British, or German, required onboard fire marshals. The National Advisory Committee for Aeronautics, the predecessor of NASA, was brought in to help solve the cooling problem. In June of 1944, a B-29 arrived at the NACA's Aircraft Engine Research Laboratory in Cleveland, Ohio. Teams of researchers attacked the problem from multiple angles, using wind tunnels, test stands, and flight testing to understand exactly why the R-3350 ran so hot. What they discovered confirmed what many had suspected. The design of the cylinder heads did not allow for enough heat dissipation. The surface area of the cooling fins was simply insufficient for the amount of heat being generated. Researchers designed new elongated cylinder heads with additional surface area to disperse the heat more effectively. The carburetor problem was also addressed. Engineers designed a new impeller to increase injection flow and create uniform fuel supply to all cylinders. No more lean cylinders backfiring while rich cylinders fouled their plugs. Wind tunnel studies revealed that the exhaust area was not getting enough airflow, so new baffles were designed to direct cooling air specifically to that critical region. The cowl flaps were redesigned to increase cooling air without adding excessive drag. A B-29 was modified with these improvements installed on its two left engines, while the right engines remained unmodified for comparison. Test pilots flew the aircraft 10 times over Cleveland, testing different combinations of modifications. The results were dramatic. With proper fuel mixture and cowl flap settings, the modified engines achieved maximum range on every flight. The baffles and fuel injection impeller increased cooling performance by 38% during periods of maximum demand. Engineers estimated this translated to an extra 10,000 feet of altitude capability or 35,000 pounds of additional payload, the difference between a B-29 that could reach its target and one that caught fire short of the objective. But implementing these modifications across a fleet of hundreds of aircraft spread across the Pacific was an enormous challenge. Engine changes had to be performed in the field, often with improvised tools and equipment. Spare parts had to be shipped thousands of miles by sea. Maintenance crews worked around the clock in conditions that would have been considered unacceptable for civilian mechanics. Yet gradually, the modifications were implemented. Engine management procedures evolved as well. Pilots learned to balance power settings carefully, avoiding the temperature spikes that could trigger the cascade of failures leading to fires. One of the most elegant solutions came not from the laboratory, but from the field. A technician studying the pattern of engine failures noticed something curious about the hottest cylinders. They were not just the rear cylinders behind the front row. They were specifically the cylinders positioned behind certain engine accessories, where airflow was disrupted even further. The solution he proposed was deceptively simple: better oil distribution to the hottest components. Improved lubrication meant lower friction, which meant less heat generation. Oil also carried heat away from critical parts. Testing confirmed his observations. Temperature sensors showed the rear cylinders running 100 to 200 degrees hotter than the front row, with cylinders behind accessories particularly affected. The ultimate fix for the fuel distribution problem came near the end of the war in the form of direct fuel injection systems manufactured by Bendix Stromberg. These systems eliminated the carburetor entirely, injecting precise amounts of fuel directly into each cylinder. No more pooled fuel in the induction system to ignite during backfires. No more uneven mixtures across the 18 cylinders. Each cylinder received exactly the fuel it needed. General Curtis LeMay, who had taken command of the B-29 bombing campaign, insisted that direct fuel injection be fitted to the Silverplate B-29's of the 509th Composite Bomb Group, the unit tasked with delivering atomic weapons. He refused to risk the most important missions of the war on carbureted engines. The transition from carburetors to fuel injection represented a fundamental shift in aircraft engine technology. Decades later, direct fuel injection would be hailed as cutting-edge automotive technology. But crews flying over Japan in 1945 were already benefiting from this innovation. There was another modification that made a significant difference, one that addressed a fundamental design flaw in the original R-3350. In the standard configuration, the front row of cylinders had exhaust ports facing forward, with exhaust pipes leading to a collector ring ahead of the engine. This meant that cooling air entering the nacelle immediately encountered a red-hot exhaust manifold before it ever reached the cylinders. The rear row had exhaust ports facing aft, which was logical, but the front row configuration actively fought against the cooling system. Exhaust manifolds are vulnerable to cracks and leaks from vibration. When a front exhaust manifold failed on an R-3350, white-hot flames would spray directly at the cylinder heads, causing valve failures and catastrophic engine fires. The solution was to redesign the front row cylinder heads with rear-facing exhaust ports. This required complex exhaust pipes that snaked between the rear cylinders, but it meant that cooling air could reach the cylinders without first passing over glowing hot exhaust collectors. These redesigned engines were installed in late production B-29's, built in 1944 and 45. Photographs of B-29 formations often show aircraft with broad bands of black staining their wing surfaces behind the nacelles. These were not identification markings, they were oil stains. The R-3350 leaked oil prodigiously, a result of the constant vibration that loosened hose clamps and fittings. Routine post-mission maintenance involved tightening dozens of connections, and if the wing surface looked like that, imagine the scene inside the nacelle. Oil fires fed by magnesium components were often more deadly than fuel fires. The human cost of the R-3350's development cannot be measured in statistics alone. Behind every one of those 267 operational losses was a crew of 11 men. Many died in fires that gave them no chance of escape, flames consuming their aircraft faster than they could reach the exits. Others survived crash landings only to succumb to burns. The emergency ditching procedures that crews practiced over and over again were rendered meaningless when an engine fire burned through the wing spar in the seconds it took to reach water. Flight engineers developed an almost superstitious relationship with their engines. They learned to read the sounds and vibrations, detecting the subtle changes that might presage catastrophic failure. A slightly rough idle, a momentary spike in oil temperature, an unusual harmonic in the engine note, these could be warnings or they could be nothing. The stress of constant vigilance took its toll. Some flight engineers developed nervous conditions that ended their combat careers. Others simply learned to live with the knowledge that at any moment their aircraft might become a flying crematorium. The maintenance crews on the ground faced their own challenges. R-3350s were so unreliable that average engine life was just 265 hours before requiring replacement or major overhaul. Some engines never even made that. Mountains of discarded radials became standard features of B-29 bases across the Pacific. Wright was producing replacement engines as fast as possible, so it often made more sense to install a new engine than to attempt field repairs. The Tinker Field facility in Oklahoma overhauled over 38,000 R-3350 engines between December 1943 and December 1952. Yet, despite all its problems, the B-29 achieved what it was designed to do. Starting in November of 1944, massive formations of superfortresses began systematic attacks on Japanese industrial cities. The strategy evolved from high-altitude precision bombing, where the engines struggled most severely, to low-altitude night incendiary raids that proved devastatingly effective. These lower-altitude missions reduced stress on the engines somewhat, though they exposed crews to more intense anti-aircraft fire. The firebombing campaign that followed was among the most destructive in human history. On the night of March 9, 1945, 300 B-29s dropped incendiary bombs on Tokyo, creating a firestorm that eliminated 16 square miles of the city. The R-3350s that powered those bombers were still problematic, still prone to overheating and fires. But the modifications implemented over the previous year had made the difference between an aircraft that usually completed its mission and one that rarely did. The final vindication of the B-29 came on August 6, 1945, when a Silverplate Superfortress named Enola Gay released an atomic bomb over Hiroshima. 3 days later, another B-29 named Boxcar dropped a second atomic weapon on Nagasaki. The R-3350 engines on those aircraft, equipped with direct fuel injection and all the modifications that 18 months of desperate engineering had produced, performed flawlessly. There is a certain irony in the fate of the R-3350 after the war. The same engine that had proven so unreliable in combat became the gold standard of commercial aviation in the 1950s. Lockheed Constellations and Douglas DC-7s, the queens of long-range air travel before the jet age, were powered by R-3350s that operated for thousands of hours between overhauls. The difference was not the engine itself, which had been continuously improved throughout the war, but the conditions under which it operated. Commercial R-3350s were flown by experienced airline pilots who managed their engines conservatively. They were maintained by professional mechanics in clean hangars with proper tools and equipment. They were loaded and operated with one eye on economics and another on safety margins. The wartime R-3350, by contrast, had been pushed beyond its limits by young pilots barely out of training, maintained by mechanics working outdoors in tropical heat or Pacific rainstorms, loaded to maximum gross weight for missions that demanded maximum performance from takeoff to bomb release. The engine was never designed for such abuse. That it performed as well as it did was a testament to the engineering improvements implemented under impossible time pressure. The corporate legacy of the R-3350 was less favorable for Curtiss Wright. While the engine continued in production through the late 1950s, powering military aircraft like the Douglas A-1 Skyraider and the Lockheed P-2 Neptune, the company never recovered its reputation. Neither the Curtiss nor Wright divisions were invited to participate in the jet age. The management failures and quality control problems revealed during the war had poisoned relationships with the military services that would define aviation's future. The company that had built the engine for Lindbergh's transatlantic flight faded into irrelevance as Pratt & Whitney, General Electric, and newcomers like Rolls-Royce dominated jet engine development. The lessons learned from the R-3350 program influenced aircraft engine development for decades. The importance of adequate cooling, the value of direct fuel injection, the need for quality control in manufacturing, the dangers of rushing complex systems into production, all were demonstrated at terrible cost over the Pacific. Modern jet engines, with their computational fluid dynamics modeling and extensive testing regimes, owe something to the engineers who struggled to make the R-3350 work when failure meant death. Boeing, by contrast, emerged from the war stronger than ever. The company had gotten the B-29 airframe basically right from the beginning, with few significant changes required to the aircraft's structure or aerodynamics. The problems had been almost entirely with the engines that Boeing had no control over. The Superfortress led directly to the B-50 bomber and the C-97 transport, and the expertise gained informed the development of the legendary B-52 Stratofortress, which remains in service today. If you have made it this far, you clearly appreciate detailed historical content. Please subscribe if you have not already, share this video with others who love aviation history, and leave a comment about what topics you would like to see covered in future videos. The story of the Wright R-3350 is ultimately a story about the tension between urgency and engineering reality. In peacetime, the engine would have spent 5 years in development, its problems identified and solved before it ever saw production. But war does not wait for engineering perfection. General Arnold's insistence that he needed the B-29 for this war, not the next one, drove decisions that cost lives, but also arguably shortened the conflict. The men who flew and maintained the B-29 understood this calculus even as they lived with its consequences. They knew their aircraft was dangerous. They knew the engines could betray them at any moment. But they also knew that strategic bombing of Japan was essential to ending the war, and the B-29 was the only aircraft that could do it. So they climbed into their Superfortresses day after day, trusting their lives to engines that had been designed by one immigrant genius, stripped of his features by corporate bureaucrats, rushed into production by workers scraping by on inadequate wages, and finally improved through trial and error in the cruelest possible laboratory, actual combat. The R-3350's cooling fins deepened by 30% in later production. The sodium-cooled exhaust valves designed to withstand temperatures that would have destroyed conventional valves. The direct fuel injection systems that eliminated the deadly backfires. The redesigned cowl flaps that balanced cooling against drag. The new impellers that distributed fuel evenly across 18 hungry cylinders. Each modification represented a small victory against physics and thermodynamics wrested from the R-3350 by engineers working against time and gravity and fire. The test pilots who died refining the design, Eddie Allen and his crew chief among them, gave their lives so that the problems could be understood. The maintenance crews who worked through Pacific nights, racing to prepare aircraft for morning missions, kept the bombers flying despite parts shortages and impossible conditions. The flight engineers who watched their temperature gauges with religious intensity, coaxing a few more hours of life from engines that wanted to quit. They were all part of the engineering process, even if their names never appeared on patents or technical papers. In the end, the Wright R-3350 Duplex Cyclone became what it was always meant to be, one of the most powerful and capable radial engines ever built. The war versions, flawed and dangerous as they were, proved that the fundamental concept was sound. The post-war developments, particularly the turbo-compound versions that recovered energy from exhaust gases, pushed the engine to nearly 4,000 horsepower and remarkable fuel efficiency. These engines flew until the jet age made piston airliners obsolete, and even then, they continued in military service for decades more. The B-29 itself has largely vanished from the skies. Of the nearly 4,000 built, only 2 remain airworthy today. Treasured artifacts maintained by dedicated volunteers who keep alive the memory of what these aircraft accomplished. When you hear the distinctive sound of 18 cylinders firing in a twin-row radial, that deep, syncopated rumble that seems to shake the air itself, you are hearing the voice of an engine that was born in crisis, baptized in fire, and ultimately redeemed through the relentless pursuit of engineering solutions to problems that seemed insurmountable. The R-3350 killed men. That terrible truth cannot be ignored or softened. But it also carried men to targets that had to be destroyed, supported a bombing campaign that contributed to ending the deadliest conflict in human history, and delivered weapons that changed the nature of warfare forever. The engineers at Wright Aeronautical, at the NACA laboratory in Cleveland, at Boeing in Seattle and Wichita, and in maintenance hangars across the Pacific, they did not create a perfect engine. They created an engine that was good enough, made it good enough through sheer determination when the alternative was failure. that is perhaps the most important lesson of the R-3350. Engineering perfection is a luxury of peacetime. In crisis, good enough must suffice, and good enough requires every ounce of ingenuity and courage that human beings can summon. The Wright R-3350 demanded that courage from everyone who designed it, built it, maintained it, and flew behind it. Some paid for that courage with their lives. Their sacrifice ensured that an imperfect engine could power a decisive weapon in a war that had to be won. The polished aluminum B-29'S that fill archival photographs gleaming in Pacific sunlight, their four nacelles humming with barely contained power, they were beautiful machines. But they were also dangerous machines, constantly threatening to become their crew's executioners. The men who mastered them, who learned the rituals of temperature management and cowl flap adjustment and engine monitoring, they were not just pilots and engineers. They were participants in one of the great engineering struggles of the 20th century, a struggle conducted not in laboratories, but in combat, not over years, but over months, not with unlimited resources, but with whatever could be scrounged and improvised and manufactured under impossible deadlines. The B-29 flew its first combat mission in June of 1944. 14 months later, the war was over. In that brief span, an aircraft that had seemed destined for failure became the weapon that ended the Pacific War. The Wright R-3350, for all its flaws, for all the lives it cost, for all the engineering compromises it embodied, proved adequate to the task. Not perfect, never perfect, but adequate, which in wartime is the highest praise any machine can earn. When the last B-29'S flew home from the Pacific, their R-3350s, smoking and leaking oil as always, they carried with them the knowledge that American engineering could rise to any challenge, however desperate. That legacy outlasted the aircraft themselves, outlasted even the piston engine era, becoming part of the institutional memory that would send Americans to the moon and beyond. The R-3350 was not NASA's finest hour. But without the lessons learned in trying to make it work, there might never have been a NASA at all. The skies above America are quiet now, free of the thunder of 18-cylinder radials straining at maximum power. The Pacific Islands, where B-29'S once struggled into the air, are peaceful, their coral runways reclaimed by vegetation. The men who flew those missions are mostly gone, taking their memories of heat gauges and fire warnings and the constant fear of engine failure with them. But their story remains, preserved in technical reports and maintenance logs, and the fading photographs of young men standing beside enormous aircraft, facing an uncertain future with courage that defied reasonable calculation. The Wright R-3350 Duplex Cyclone was never the engine its designers hoped it would be, at least not during the war that made it necessary. But it became the engine that history demanded, transformed through crisis into a tool of victory. That transformation cost too much. It always costs too much. But the engineers who achieved it, who took a flawed design and made it work through force of will and technical brilliance, they deserve to be remembered alongside the pilots and gunners and bombardiers who trusted their work. They fought a different kind of war, a war against physics and metallurgy and corporate dysfunction, and they won. The B-29'S that flew over Japan were their victory as much as any combat medal could signify. The story of the R-3350 is not a story of triumph. It is a story of struggle, of loss, of desperate improvisation, in the face of deadlines that could not be moved and enemies that would not wait. But it is also a story of human capability, of what engineers can accomplish when failure is not an option and the stakes are measured in lives. Every B-29 crew that returned safely from a mission over Japan owed their survival in part to the engineers who had made their engines slightly less likely to explode into flames. That is not the kind of debt that can ever be fully acknowledged, but it can be remembered. And in remembering, we honor not just the crews who flew, but the engineers who gave them a fighting chance to come home